In this video, we're going to be looking at independent relative motion. And so this is when you start to look at two particles that are moving independently. So their movement has nothing to do with the other particle. So two particles with independent motion. But sometimes it's very convenient to see how does that motion relate to, how does the motion of one particle relate to the motion of the other particle. And so you'll see how this becomes really handy. But so far, when we've looked at problems, we've said it's really important to set an origin and a coordinate system. So I'll do a really simple one here. Let's say we set an origin here, we'll set an origin here, and we'll set a coordinate system of x going across. So this is our coordinate system and our origin. And if we set a particle here, let's call it particle A, the position of particle A from the origin would just be xa. It would be the distance here, xa. And we're actually going to call that the absolute position of particle A. And it's the absolute position because it's measured from the origin. But let's say we introduce that second particle, we'll call it particle B, and it's here. The absolute position of particle B will come from the origin and would be this distance here. This would be xb. So xb is the absolute position of particle B. Measured from the origin. But there's another way to look at the position of these particles. You could also say, what if we set a coordinate system starting at particle A? So what if we said we start a new coordinate system, x prime, that starts here at particle A, and we'll call that x prime. So x prime is the coordinate system fixed to particle A. Now we can actually define a position of particle B relative to particle A. So we could say here, I'll use blue, this distance here would be the position of particle B relative to A. So xb relative to A is the position of particle B relative to A. If we look at these position vectors that we've drawn here, you can see that if you had xb minus xa would give you this xb over a. So I'll rewrite that as an equation. So we can say xb relative to a is equal to xb minus xa. Now, and I'm just going to move this up for a second. You'll never really see it written this way, but there's sort of an invisible, you could rewrite this equation as xb over a is equal to xb relative to o minus xa relative to o. So what this is saying here is this is the position of xb relative to the origin, or the position of a relative to the origin. We almost always drop this o here because it's redundant, but that's what it's saying. And so if you're not sure which order to put, so if you're like, oh, do I say xb relative to a or xa relative to b, the position that you're looking at is always on the numerator relative to the denominator. So actually, I'll just erase this and I'll rewrite this for your reference here. So if you see xb relative to a, this is saying the position of particle B relative to the position of particle A. I'm going to move this up again and rewrite the equation. We have xb relative to a is equal to xb minus xa. If we take the derivative of both sides of this with respect to time, we would end up with the velocity of b relative to a is equal to the velocity of b minus the velocity of a. If we took the derivative again, we would end up with the acceleration of b relative to a is equal to the acceleration of b minus the acceleration of a. So these equations hold true for position, velocity, and acceleration. If, and only if, both particles are moving at a constant acceleration, you can use the relations of uniformly accelerated motion. I copied those equations out for you just as a reference, but they're the same uniform acceleration equations that we used before. Just make sure that you're consistent. So you can't say xb is equal to xb over a naught plus xa over b naught t. Whichever variable you're using has to be the same variable for all equations. So essentially make sure that you would have the same subscript for all of them. Now we're going to do an example, so I'm just going to erase the screen and write out the problem. Before we get started on this example, I forgot to mention something super important. When you have independent relative motion, in fact for all of these problems, you always want to have one origin, and one clock. So the time for both particles has to start at the same time t naught, and you have to have one origin that their absolute motion is relative to. So this is just really important, and I'll show you what that means right now. So for this question here, the question is saying we have two fireworks that are launched. Rocket A is launched with an initial velocity v naught equals 100 meters per second. Rocket B is launched t1 seconds later with the same initial velocity. The two rockets are timed to explode simultaneously at a height of 300 meters. At this moment, A is falling and B is rising. Determine the time t1 and the velocity of B relative to A at the explosion. So let's draw our picture. So I'm going to set the origin at the ground. So the origin is here at the ground for both particles. I'm going to set upwards as the positive direction, positive y. That's our coordinate system. Now for firework A, it's being launched upwards and then it's coming down and exploding. It has initial velocity v naught equals 100. Rocket B is being launched with the same velocity and it's exploding on its way up here. So it also has v naught equals 100 meters per second. This height here is 300 meters. So that's graphically what's happening in this picture. What else do we know about the motion of the fireworks? Well, we know that their acceleration is equal to gravity, which is equal to negative 9.81 meters per second squared. It's negative in this case because we set our coordinate system here as positive upwards. So if the acceleration of the particle is equal to negative 9.81 meters per second squared, that means it's not changing with time. No matter what time it is, no matter where the particle is, this acceleration is not changing, which means we can use our constant acceleration equations. So that means that the velocity is going to be equal to v naught plus the acceleration times time. So the velocity of our rocket A, VA, is going to be equal to its initial velocity, which was 100, minus 9.81 t. The position of particle A can also be determined from our constant acceleration equations. So we also have y is equal to y naught plus v naught t plus 1/2 at squared. So our position of the rocket A is going to be equal to ya naught, which was 0 because it's at the origin, plus its initial velocity times time, so it's plus 100t, minus half of the acceleration t squared, so minus 4.905 t squared. So from this equation, we can actually tell that we're able to find the time t when the firework A explodes, because we know that it happens when ya is equal to 300. So we'll have 300 is equal to 100t minus 4.905t squared. In this case, we'll use the quadratic equation. I'm going to move this upwards. So now we have the quadratic equation, which in case you don't remember is minus b plus or minus b squared minus 4ac square root divided by 2a. From here we end up with t is equal to 16.7 seconds and 3.65 seconds. So from this, which t value do you take? You're going to take the second t value, because the first time, and I'm just going to show you on this drawing up here, the first time it passes the height of 300 meters, it doesn't explode. It explodes the second time it passes that height. So for firework A, it's going to explode at 16.7 seconds. But the second firework has the same type of motion, has the same initial velocity and the same acceleration. So the time when the second firework explodes is going to be this first time value. So if we want to find the time lag when the second firework exploded, t1 is going to be equal to 16.7 minus 3.65, which is going to be 13.1 seconds, which is that time lag. To calculate the velocity of B relative to A at that moment, we calculate, I'm going to move this up, we calculate VA at that moment and VB because we have an equation for the velocity. So VA is equal to 100 minus 9.81 times 16.7 seconds is equal to negative 64.1 meters per second. This makes sense because our particle is moving downwards, which means the velocity should be negative. So this kind of confirms that we're on the right track. Velocity B at that moment will be 100 minus 9.81 times its time, which at that moment is 3.6 seconds, which is equal to 64 meters per second. That's a positive number, which means the velocity is going up, which makes sense with our physics at that moment. So our relative velocity is going to be VB relative to A is equal to VB minus VA, which is equal to 64 minus negative 64.1, which is equal to 128 meters per second upwards. This is saying that from the perspective of particle A, particle B looks like it's moving 128 meters per second upwards. So particle A is coming down, and it looks like particle B is moving twice as fast in the upwards direction.